So here's method number 1. Gather a sample and then just perform this calculation. So in other words, take the mean of your sample, subtract the mean of the population, and the difference is your measure of sampling error. But you should recognize right now that there's a problem with performing this calculation. So the problem is we would need to know mu, right? In order to perform this calculation, we need to know mu. All right, well, we don't know mu 99.99999% of the time. So how can we perform this calculation if we don't know mu? But then the other thing is, okay, wait a second. Even if, let's just pretend for a second, we did know mu. Well, if we know mu, why would we be using x bar to estimate it, right? If we already know mu, then why calculate x bar? You see how this is stupid for 2 reasons, right? And again, the 2 reasons are we don't know mu 99.999% of the time. And the second reason, if we did know mu, we wouldn't be calculating x bar. So this is why this method gets a thumbs down. But it does help you to understand sampling error, right? Think of the dart and the bullseye. So x bar is the dart, and mu is the bullseye. And the difference between them is sampling error. So that's going to be huge in my case. We're playing dart. So onward to method number 2. Now, we'll look at this, but I'm going to take it apart and explain it. So don't worry if you don't understand what this is saying here. I don't expect you to. But this says calculate the standard error of the mean, and that's just abbreviated to SEM. So we're going to calculate SEM from a sampling distribution of the mean. Now, I notice how I emphasize the ing. I said sampling distribution. And that's because this is a very special distribution. It's not just, for example, a distribution of all your scores. Okay? You're going to learn it's a distribution of x bars. We'll get to that. And then I'll also explain why SEM, like what it is, and why it's a measure of sampling error. But first, you have to understand the concept. And that concept is when we have a lot of variability in our estimates, that means there's a lot of error. Okay, so again, when we have a lot of variability in our estimates, we have a lot of error. So I'm going to go through the analogy that I talk about in the book because I think it's a good way to understand sampling error. This is just an analogy. We're not actually sampling here, but it's a good analogy to help you understand. So let's say you go to Walmart and you buy the cheapest scale they have, $7.99 rollback special, okay? And you want to know how much you weigh. So you wake up in the morning, you go pee, don't get dressed, don't do anything, just step on the scale, okay? And let's say it tells you weigh 100 pounds. Step off the scale and get back on right away. And this time it says you weigh 80 pounds. And then step off, step right back on, and this time it says you weigh 115. And then for the 4th time, you get off, get back on, it says you weigh 140. By this time, you've given up, right? Do you have any sense of what you weigh? These are all estimates of your weight, right? Because it's a cheap scale, right? So these are only estimates of your weight. And you really have no idea because of what you weigh, because none of them agree. They're all really far off from each other. If we were to measure the variability of these estimates, let's say using variance or standard deviation, we would see that the variability is high. In other words, there's lots of error. You wouldn't say that this scale is accurate. You would say this scale sucks, and you would take it back to Walmart. Okay, it's no good, doesn't tell me how much I weigh. There's inconsistency in the estimates. So you return it, and this time, so here's that take-home message, right? A lot of variability among the estimates means that you have a lot of error. Okay, you take the scale back, and this time You buy a very, very expensive medical grade scale. I don't know, you paid $500 for this thing. And same thing, you wake up in the morning, you go pee, don't get dressed, step on the scale, tells you weigh 110. Then you step off, get right back on, this time 110.5, then 109.5, and then 110. Do you have any idea how much you weigh now? Well, of course you do, because these estimates are very close to one another. There's a lot of consistency. In other words, there's not a lot of variability. If you were to measure variance or standard deviation of these numbers, you would get a small answer, right? Your answer would be small. And so what this is telling us is that when there's very little variability among the estimates, there is very little error. So now you're going to learn how SEM is simply a measure of variability of your estimates. So we're going to be estimating X bar. We're estimating mu using X bars, right? We're going to take a whole whack of X bars, and then we're just going to measure the variability among those X bars. And that gives us SEM. And that means if we have a small SEM, it's like this case, right? Pretend these are all X bars. And we're going to use that statistic, SEM, standard error of the mean. We're going to look at the variability among these estimates. We get a small number. That means there's very little error. However, if we were to get a bunch of X bars and they all disagree with one another, SEM will be a high number, and that means there's a lot of error. Okay?